Section 1. What if I told you someone topped the HuggingFace Open LLM Leaderboard, one of the most watched benchmarks in the AI world, using 2 gaming GPUs you can buy at your local electronics store? No data center, no TPU pod, no million-dollar compute budget. Just 2 consumer-grade cards and a very clever engineering approach. This is the story of how a developer called dnhkng did exactly that, and what it actually means for the rest of us. So, what did this project actually do? At its core, it achieved a top-ranked score on the HuggingFace Open LLM Leaderboard, a public benchmark that evaluates large language models across a battery of standardized tests, including reasoning, knowledge, and language understanding tasks. The leaderboard is dominated by submissions from well-funded labs and companies running serious hardware. Getting to the top is treated as a signal that you have both the model quality and the compute to back it up. The trick here wasn't a new architecture from scratch. It was a combination of aggressive quantization, strategic model selection, and pipeline optimization that allowed the model to run inference across 2 consumer GPUs, likely something in the RTX 3090 or 4090 class, in a way that preserved enough performance to score at the very top of the leaderboard at the time of submission. Quantization, if you're not familiar, is the process of reducing the numerical precision of a model's weights, going from 32-bit floats down to 8-bit or even 4-bit integers. Done naively, this tanks performance. Done carefully, you can get surprisingly close to full precision results at a fraction of the memory cost. That memory savings is what makes running a large model on gaming GPUs feasible in the first place. The author combined this with careful selection of a base model that was already well optimized, then ran it in a split configuration across the 2 GPUs, essentially distributing the model's layers so both cards share the workload. The result? Leaderboard topping benchmark scores from hardware that costs a few $1,000s total. Let's be clear about what actually happened here. The benchmarks were real. The score was real. The hardware was real. This wasn't a trick submission or a cheat. It was smart, disciplined engineering. Section 2. Now let's talk about what this did not do, because this is where honest context matters. First, and this is important, topping a benchmark leaderboard is not the same as building the best AI system for real-world use. The HuggingFace Open LLM Leaderboard measures performance on specific standardized tasks. These tasks are well-defined, closed-ended, and repeatable. Real-world use cases, customer support, coding assistance, document analysis, involve messy, open-ended inputs that benchmarks don't capture. A model that scores 90 on a benchmark might be mediocre in production. A model that scores 75 might be excellent for a specific domain. Second, this setup is not production ready for most teams. Running a large model across 2 gaming GPUs in a home lab or enthusiast setup is impressive. Scaling that to serve hundreds or thousands of concurrent users is a completely different engineering problem. Gaming GPUs aren't designed for the duty cycles of production inference workloads. Thermal management, uptime guarantees, and throughput at scale are all challenges this project doesn't address. Third, the leaderboard position is a snapshot in time. These rankings shift constantly. New models and new submissions arrive weekly. The point isn't that this project permanently dominates, it's that it demonstrated it was possible at all. Fourth, quantization has real trade-offs. The memory savings come at a cost. In some tasks, particularly those requiring precise multi-step reasoning or nuanced factual recall, quantized models do degrade compared to their full precision counterparts. The degradation might be small, but it's not zero. This project made a bet that the benchmark tasks wouldn't expose that gap significantly, and the bet paid off. That won't always be the case. So, impressive engineering achievement, real result, real limitations. Section 3. What could this approach realistically enable in the future? Here's where things get genuinely interesting, and I'll keep this grounded. The most immediate practical implication is for solo developers and small teams. Right now, if you want to run a capable open source LLM locally, whether for privacy reasons, cost reasons, or latency reasons, your options are limited by your hardware. Projects like this one demonstrate that the gap between consumer hardware and enterprise-grade AI capability is narrower than the marketing suggests. As quantization techniques improve and tooling matures, things like GUF, Llama CPP, Llama v2 will likely see more developers running genuinely powerful models on machines they already own. For organizations that handle sensitive data and can't send prompts to cloud APIs for compliance reasons, this is directly relevant. A well-optimized model running on local hardware is a real alternative to cloud inference for many internal use cases. document summarization, code review assistance, internal search. The engineering to make this work is getting more accessible every month. There's also a research signal here. If consumer hardware can reach benchmark competitive performance today, what does that mean for AI accessibility in 2 or 3 years? As GPU memory continues to grow and quantization methods continue to improve, the compute requirements for frontier level local inference will keep falling. That's not speculation. It's an observable trend. One realistic near-term application: small AI startups that want to offer self-hosted model deployments to enterprise customers who don't want their data leaving their infrastructure. Instead of requiring a rack of A100s, they could potentially offer deployments on more modest hardware. That changes the economics significantly. If you're building that kind of product and need reliable hosting for the surrounding infrastructure, the API layer, the user dashboard, the model serving endpoints, that's exactly where a platform like DigitalOcean becomes practical, since it lets you deploy and scale the surrounding stack without managing raw hardware. Section 4. So why does this project exist? What problem is it actually solving? The honest answer is, it's solving a perception problem as much as a technical one. There's a widespread assumption in the AI industry that serious model performance requires serious hardware. That assumption is reinforced by the fact that the big benchmark leaders are almost always large labs: OpenAI, Google, Meta, Mistral, with corresponding compute budgets. This creates a mental model where consumer hardware is for experimentation and toys, and real AI is done in data centers. This project challenges that assumption directly, not by claiming consumer hardware is equivalent to a data center, it isn't, but by demonstrating that with the right engineering choices, you can reach a level of performance that the industry treats as a signal of seriousness on hardware that an individual can afford. That matters for a few reasons. It matters for developers who feel locked out of the top tier of AI capability by budget. It matters for researchers in lower resource environments, universities, independent labs, small companies who want to contribute to open model development without requiring institutional compute grants. And it matters as a counterweight to the narrative that AI progress is exclusively a function of how much money you spend on GPUs. The developer who built this didn't do it because they needed to top a leaderboard for business reasons. They did it because they wanted to know if it was possible. That kind of curiosity-driven engineering is exactly what keeps the open source AI ecosystem from being completely outpaced by well-funded incumbents. And the answer, it turns out, is yes. With smart engineering, 2 gaming GPUs is enough, for now. The ceiling keeps moving, but so does the floor.